And now to our second guest. It's not often that we are able to turn natural flaws into technological advantages. Our next speaker will discuss how defects in materials can be integrated into the design of a quantum computer. Please give a very warm welcome to Maria Viitaniemi.
I need that. I do need that though. Testing. Good job on my last name. So like she said, my name is Maria Viitaniemi, and I'm a physics graduate student at the University of Washington. And today, I want to tell you guys about the future of computers. But before we go more into that, I have a question for you. Does anyone know what this is? Anyone? Take a guess.
It's a computer.
It is a computer, in fact. And this is the first modern computer called the ENAC, made in 1946. You were close. And it was about the size of a 2-bedroom apartment, and it was made out of 18,000 vacuum tubes, which are devices like this that are used to carry the electricity throughout the computer. It was used to calculate the trajectories of ammunition over and over again with different input parameters. Okay, another question. Anyone know what this is? What do you think, Arjun?
Cash register.
Telex or Twix?
Good guess. This is actually,
A Telex or Twix?
close, maybe. This is actually the first modern desktop computer called the Programma 101. It was made in 1964. And like the ENAC, it could calculate math problems over and over again. And at the time, it was so useful, in fact, that NASA bought 10 of them to use for its Apollo 11 mission. So, things have been changing a lot in the last 70 years. We've developed computers from the ENAC to the Programma, on and on. And how many of you guys are like me and use your little mini computers, like iPhones, way too much? And why not? They do a lot. You can go on the internet, you can play cool games, all kinds of things. But in fact, they're not perfect. There's a lot of things our modern computers don't do very well. And one of those things that they don't do well is they're not very good at factoring numbers. Do you remember what that is? So when you take a number, like 6, and you split it into the products, and when multiplied together, equal that original number. So for 6, that's not very hard, 3 times 2. But you can imagine that it becomes much more difficult to find those two numbers when your number is 16 digits long. Our modern computers are very inefficient at solving this problem. But who cares about factoring large numbers besides some mathematicians? Actually, most of you guys do. I don't think this is doing anything. Can you guys still hear me?
Yes.
Cool. So, all of us care about it a lot. Because this problem of factoring large numbers is the basis for a lot of our public encryption. So one of the most common public encryption systems, the RSA, utilizes this problem of factoring large numbers in order to securely store and send public data. And we all have seen in the news lately what goes wrong when our data is not securely sent. Even our own government has been hacked. So this is a big problem, okay? So we look at our modern computers and they're not doing so hot. They can't solve some very simple math problems. They can't send our data securely. What are we gonna do about it? How are we gonna solve this problem? And the thing is, our modern computers actually are pretty good at what they do already. We've been working on them for 70 years. So we're gonna have to change something pretty drastic, something pretty fundamental about our computers to make them better, to be able to solve these problems. And what that is becomes evident when we think about another problem that modern computers have. Something else that we'd really like to do that's really inefficient right now is modeling really small things. So things that are the most fundamental building blocks of everything around us, called atoms. Atoms are so small, in fact, that if you were to take 100,000 of them and put them all in a line, all in a nice little row, they would be about the width of a single human hair. That's really tiny. And when things get that small, they get kind of weird. So, for example, if I take a big thing, like an apple, and drop it, we learn in Physics 101 that you can describe that apple's position very accurately using one equation involving its speed and its acceleration. But if we take something really tiny, like an atom, and we drop it, we can't use that same equation to describe it anymore. In order to describe it accurately, we have to consider the fact that it might fall, but also that it might fly to the left, or fly to the right, or do a little dance. And I'm not telling you your atoms are going to start dancing. They might. Unlikely, but they might. And we have to consider that unlikely probability if we want to describe it accurately. And so this math to describe these atoms is so different. We give it its own name called quantum mechanics. And so we can actually solve one atom. It's okay. But what if we want to solve a couple atoms, maybe a couple different atoms? And then we have to consider the possibility of what everything's going on. They're all interacting with each other. What might they do? This problem starts to take a long time for modern computers to solve. It's pretty difficult. And actually, that's something that a lot of people want to do. For example, biologists would love to model proteins, the building blocks of all living things. And right now, it's actually so difficult for them to do it. It's so slow on our modern computers that they've created apps asking regular computer users like you to donate the time on your computers so they can model more of these, so they can do what their research. And it's still really slow. Really, really slow. You can ask my friend, he's laughing right there. And so what are we going to do? And if they could do this, if they could model these proteins better, they could develop drugs, medicine, without side effects. Wouldn't that be great? And so it looks like I've told you some more problems with modern computers, some more things we can't do. That's not looking so hot. But scientists are taking one of these problems, this complexity of quantum mechanics, this difficulty in modeling small atoms, and we're trying to use it to our advantage. We're trying to develop a new kind of computer, and it'll use this quantum mechanics to its advantage, and so we're going to cleverly call it a quantum computer. Awesome! A quantum computer. It's going to solve all our problems. Now the question is, what's a quantum computer? What's it going to look like? Who's developing it? What are we going to do? And well, you can go in my lab, and you can see something like this. Or you can Google online, and you can see something like that. And I must admit, these are not quantum computers. These are machines used trying to study small pieces of things that will eventually be used in a quantum computer. And so we're not quite there yet. But from nothing in 20 years ago, we've come a long way, and developments are only getting faster. And so I'm really excited for the prospect of what quantum computers are going to be, what's coming up in our future. And I want to get you guys excited too. So I want to tell you guys a little bit more about what exactly makes quantum computers so special, how we're planning on making it. But before I can tell you more about quantum computers, let's take a step back and talk a little bit about how our regular computers work. So let's take our regular computer, and we want to do something simple, like type the word hello. Okay? So we have to take each of the letters in hello, and we need to represent it with a code that the computers can understand. So we're going to represent them with a series of ones and zeros. Each one or zero is called a bit. The group of 8 is called a byte. A billion bytes makes a gigabyte, kind of like in your flash drive. And each letter has its own code of ones or zeros. And then computer scientists, they're pretty smart guys. They can take these, string a bunch of them together, make them interact with each other pretty simply, and they can do a lot of cool things, like make video games. Awesome. But now we have to ask, okay, we have ones and zeros, but that's not a thing. How do we physically represent these ones and zeros? We talk to our engineering friends. They make us some circuit boards. Electricity flowing means 1. Electricity not flowing means 0, oftentimes. And we have a regular computer. Cool. Not so complicated. Those are 3 things we need. We need a product. We need the software code that makes this product work. And then we need the hardware to physically represent this product. So what are all these things going to look like in a quantum computer? So we've talked a little bit about what we want to do. We want to do things like model proteins. Okay? But now, what makes quantum computer code different than regular computer code? What makes it special? What makes it more powerful? And to talk about this, let's take our modern computer bits. We're going to represent a 1 with a red box with its face to the right, and a 0 with a blue box with its face to the left. And quantum computers, we've decided to call them quantum bits or qubits. Physics are pretty great there. And they still have their ones, their red boxes, and they have their zeros, their blue boxes, but they can also have a special box that's both a 1 and a 0 at the same time. Notice that I said both 1 and 0. I didn't say somewhere in between. It's not we don't have a purple box. We actually have both. If you were to take a look at that or show it to someone in the street, you don't know what they would say. Did they see a red box? Did they see a blue box? It's kind of 50-50. And this special property is called superposition. This ability to be both a 1 and a 0 at the same time. It's a little confusing, so let's take a little bit more of a fun example. Raise your hand if the first thing you see when you look at this is a duck. Okay? Raise your hand if the first thing you see when you look at this is a rabbit. Usually it's about 50-50. And so in case you don't see it, those two appendages over there, those are either the duck's bills or the rabbit's ears. And so this picture, until you look at it, it really is both a duck and a rabbit at the same time. Once you show it to somebody, it becomes one or the other. So this is an idea of what superposition is. This picture is in a superposition of a duck and a rabbit at the same time. Just like our qubits, our box is both a red box and a blue box at the same time. And that's what gives it its power. Because it's in a superposition, it's kind of like it can do two things at once. So for example, if we were to take a maze in our old computers, we'd have to consider each of the different paths one at a time and go around. If it went the wrong way, it has to go back and try again. And it's pretty inefficient. It takes a long time, and it can only do one thing at a time. But if we could go in a superposition, our maze, we could try many paths at the same time. And when one doesn't work, we just keep going, and we can still keep trying many paths at the same time. This makes our computers go a lot faster. And so this is one of the powers of our qubits. And you can see that when we consider problems like this with many atoms going all different directions, it's useful to be able to try many paths at the same time. And so now we know what is going on with our software. One of the reasons why the software can start to be more powerful than our old computer software. But how many of you guys have seen something in a superposition lately? Nobody? Yeah, no, me neither. It's a little bit hard. And so one idea for how to physically represent these things is we go back to our old problem child, the atom, because we know that already works with the laws of quantum mechanics. And so we're going to take actually a small piece of an atom called an electron, and we're going to use one of its special properties to represent these ones and zeros, because it has something called a spin. It can either spin to the left or it can spin to the right. And we represent these with our ones and our zeros. And so we can take these electrons. We've actually found that if we take lasers and we shoot the right color laser pulse for the right amount of time at our electron in our atom, we can make it be in the red state or in the blue state or in a superposition of the two. And we can see that if we shine a different size laser pulse at it, we can keep controlling them, switching them back and forth, and we can start to make these computer codes. Awesome, we have all the answers, we know the code, we know what we're going to use, but atoms are really small. They're 1/100,000th the width of a human hair. How are you going to catch one and keep it there for long enough that you can shoot a laser at it multiple times and connect it with its friends? Hard. There's many solutions for this. And what my lab is doing is we talk to our friends in material science, and they're really good at playing with atoms, and they really like to arrange them in very beautiful patterns called crystals, kind of like how a kid plays with Legos. And they organize them in these beautiful patterns. They got blue and gray, and wait. They made a mistake, right? You guys see that? The orange atom that's right there? Everyone can see that, right? Yeah, looks like a problem. We call them defects. Not good, doesn't sound good, but it's pretty noticeable. It actually kind of acts differently than all the atoms around it. And so if we shoot our laser at it, we can pretty much always find that one atom. And now we have a crystal. It's kind of always held in place. We can manipulate this crystal. It's big enough to be able to hold. So now it's kind of starting to look like we can maybe use this to build a new kind of computer circuit. And so we have this now. We have one idea for this physical representation of a quantum computer. And now all our problems are solved. We know the code, we know the atom, we're there, right? That's the question. Are we there yet? Not quite. There's some problems. Our atoms, even though once we put them there and we shoot our laser at it, they don't like to stay there. They like to talk to other atoms and to the environment, and that gets them all messed up, and they lose whatever position we put them in. It's kind of a mess sometimes, and the code's a little complicated, but we've made a lot of progress, and we're still working on it. People like me are trying to find new qubits that talk to the environment less, that we can use, that will stay in those states for longer. There's people working to take the qubits we've already found and start to build these circuits so we can actually control them in useful ways and can start to connect many of them. There are people that are working on the code because once we have these computers, they want to be able to make sure that we can use them for something useful. And it's not just me in my lab, but there's universities all over the world, hundreds of thousands of graduate students working on this problem. There's also companies who are putting a lot of money into this because they truly believe that quantum mechanics, quantum computers are the future of technology. And so we're not quite there yet, but we've come a long way in 20 years. And if we as a society could go from the ENAC to an iPhone in 70 years, I have high hopes that quantum computers, we could start seeing them maybe in our lifetimes. And that's pretty exciting. So in conclusion, there's a technological revolution on the horizon. And it'll change the way that we solve the problems that we already have. It can also give us new ideas for what the problems we can even start to ask. And so with that, are there any questions for me? Thank you.
What's the scale of the devices you're talking about?
So it depends on there's lots of different options where these devices can be. And so the scale of my things is we're thinking of microns. So that's like millimicro. So that's like a 10 to the negative 6. So it's widths of human hairs, full hairs. But that's a few of those qubits. But you need like hundreds of qubits in order to make it. And right now it takes a lot of hardware to be able to control these qubits. And so that's why we're kind of at that 2-bedroom scale of things right now. Yeah.
So you said that quantum computers could make code solving a lot easier because they can crack the numbers pretty easily.
They make certain problems.
So specifically for cryptography though, if you had quantum computers, would that mean that like all of the encryption software that we have right now would just fall apart?
Yes.
So how do people want to deal with that? Is that a thing that like ethics-wise physicists think about? Or?
I don't think physicists are thinking about it so much, but I know there are larger organizations that are thinking about this. There are people who are starting to I heard that someone is asking for people to start thinking of quantum-proof ways of encrypting data.
Can I speak to that?
Yeah.
So I work for Amazon Web Services and cryptography department.
Okay.
And we have PhDs all over the world who are engaged in developing post-quantum encryption schemes. And they're actually, the way they're doing this is with contests, where they offer prizes for the most unbreakable systems.
Mm-hmm.
And they want to do post-quantum computing post-quantum cryptography now, even before there are quantum computers, because any data that we store now using encryption schemes that aren't quantum safe, will be able to be broken later as soon as the quantum computers
That's good to know.
Yeah.
Yeah.
Ahead of time. So.
Only recently, people in China, a group in China was able to send messages to a satellite and back. So it's not that far away. Yeah.
So, you're saying that they're working all over the world. I've heard that China's really into this. Like they're doing quantum entanglement, per se,
Mm-hmm.
communications and so forth. How much interaction is there with between the groups? It seems like I know Microsoft and Google might be corporate stuff, but
Yeah, so there's oftentimes large conferences, and so it kind of depends on what conference you're talking about, and it depends how many people are coming together. There's probably not as much collaboration as we would like between different countries, because there's all kinds of issues. But I mean, people do still publish in like peer-reviewed journals, and there's journals that from all different countries that we can read. So it varies. But I mean, there's scientific community is pretty good generally about publishing, and everyone thinks the same journals are important.
So you started by speaking about the proteins and modeling them.
Mhm.
You said it takes a long time. What is a long time?
I think Jacob can answer that better than I can.
Yeah, it depends on the protein and how well you're trying to model it, but we've managed to get it down to like a couple days worth of computing time, probably, on our more powerful machines.
So it takes,
Like a single computer. Yeah.
yeah. And the thing is, they have to like model it over and over again if they want to actually make something useful, right? Because you have to like test it.
Got it.
So days.
Iteration.
Yeah.
I'm wondering, like, right now, it may just be a completely, like, selfish question, but the laptop that I have, the battery just does not keep up. So it makes me wonder, like, how long, or how much power would something like this actually require? Is this something that's, in our current abilities, something that's able to be scaled down from what it is?
So, like I said, we're kind of in the 2-bedroom scale and act stage of things. And also a lot of these problems that, like I said, our modern computers are really good at doing what they do, which is things like the internet and emails and video games, which is what most of us care about. So I think in our lifetimes, the most likely use for quantum computers will be something more like research-based, like modeling proteins. I think we're a fairly long way away from actually being anything user-friendly, and we don't really even know what all the uses of quantum computers could be. So that's another thing people are still working on. What actually can we use them for, besides some of these problems that we already thought about? Yeah.
So modern computer hardware processors in particular are already encountering all sorts of problems with tunneling phenomenon and gate leakage.
Yeah.
When you try and produce a quantum computer on this sort of scale, how long are the qubits going to be stable for? Is this something that's going to have to be kept at like 1 Kelvin to function, or could this conceivably exist at room temperature?
So that's an interesting question, and that's kind of why people are considering, I talked about one specific kind of qubit, these atoms in a solid state crystal, and that's what my group is working on. And these ones are right now mostly at low temperatures. Some are liquid nitrogen temperature, so not quite as cold as liquid helium. But there's other people working on different kinds of circuits and different kinds of defects and different kinds of systems altogether. And so people are still kind of searching for the perfect qubit. So a lot of things right now do have to be cold and require a lot of hardware. So we'll have to see how things go. Yeah.
So you talked about how you use lasers to switch qubits from one state to another.
Mm-hmm.
But in most so computers, you have one bit that talks to the next bit and things like that, where you could sort of cascade.
Mhm.
Is there any way within your crystal to be able to make a particular defect talk to another defect? Or?
Yeah, so that's what the people are doing, kind of, is there a pointer? In the top right-hand corner, those kind of circuits. So those are actually like little light waveguides. And so part of the power of these solid-state crystals, that why my group has chosen to use them, is because once they do couple this like spin of the electron to a photon, and then those photons can talk to each other. That's not exactly my research. I don't know all the details of it, but that's part of the idea. They use light actually, and lasers can be used to excite them, and then there can be readout of this light that comes out of the atoms afterwards. Yeah.
You talked about like the focus of it mostly being on processing. Is there also opportunity for like really dense storage with this too?
Yeah, so that's another useful thing with a lot of our systems is that we were using this electron, but there's atoms also have a nucleus, right? So they have protons and neutrons, and so so one way of storage people are thinking about is taking this electron spin and coupling it to the nucleus's own spin, and so that'd be a long-term storage kind of thing. There's also different systems that have their own ways of thinking about long-term storage. Cool. I think that's all the time we have for questions. If you have other questions, come talk to me.